Okay, hello, welcome guys, how you doing? Welcome to the software portion of our beer cooler controller. What we're going to be doing, sorry guys, it's been taking a while to get this one out. I actually had a trip to the wonderful hospital. Yeah, great people there though, but we got a piece of metal lodged in my eye, so I actually have been under the weather for a little while. First time I've been able to actually look at the screen without squinting, so anyway, yeah, that's all over with though. I'm fine, everything's good to go. I think I mentioned it in my Twitter feed, so if those of you that aren't subscribed to me on Twitter, follow me on Twitter. I'll kind of let you know what's going on if I can. When a video is going to be late or whatever, I'll let you guys know on there, so check me out on Twitter. I'll usually put a link in the description. But anyway, back to what we are here for. We're here for the software portion. Now, I'm going to warn you, this video will probably run a little long because there's some math and whatnot involved in calculating the thermistor and whatnot. So this video might run a little long, so just be prepared. Anyway, we got our hardware pretty much done in the last video, so I'm not going to go over that, but we'll start with this picture. We got our microcontroller, our thermistor kind of set up over here, and our relay set up. So first thing we need to do is, obviously, when we are pulling in an analog value, right, we're just pulling in a scaled voltage value, right? That's what we're yanking into our analog digital converter. So what we're going to have to do is we're going to have to convert that back to basically a resistance so we can correlate it. And the reason we want to convert it back to a resistance is because, let me grab it, a wonderful data sheet for our thermistor that we got going on here. Let's scroll down. You get this wonderful table that shows you, and we're using the 2252 ohm little guys. What we're using, it shows you the correlation to degrees in Celsius, what the resistance should be. So if you're looking at, and it's usually normalized, meaning that the 2252, the 2.2K mark will be at 25 degrees, or normalized around, you know, the normal, you know, 25 degrees Celsius, or that's around 73, 75 degrees Fahrenheit is what that is. So just like normal room temperature range. Okay, so room temperature is defined to be around 25 degrees C, or like I said, 73, 75 degrees Fahrenheit. So you've got, it normalizes around that, and then it will move either up in resistance the lower the temperature goes, or it will move down in resistance the higher the temperature goes, as you can see by the numbers. So what we need to do is we need to find some sort of a correlation, and we need to calculate what happens if we're in between. What if we're like 1.5 degrees or something, or we're 25.5 degrees or something. We're in between these marks. Well, you need to decide right here now, are you wanting to just go ahead and round up to the next unit, or are you wanting to try to basically interpolate in between the two? Well, what I did was I figured, let's just make this complicated. And actually, it's not that complicated. And let's find a line of best fit for this data. So what I'm going to do is I'm going to pull up good old Excel here. Magnificent, marvelous Excel. Here, let me delete this because I want to start from scratch here. Okay, what I did was I basically just took that information. Let me pop that back up. We'll make it smaller so we can actually see both here. So all I did was I took that information and just put it over here into like an X and a Y. Okay, the X is the resistance, and the Y is going to be the temperature. That way we can plug in a resistance, because right, we know that we're putting this with a 5 kilo ohm resistor, or no, 10 kilo ohm resistor. So you can just do a voltage divider just like we do in analog digital converters. If you want to, you can watch my other videos to see, you know, how I come up with this. But we just do a volt divider across it, right? So basically to find the, you know, the voltage, and then we can Ohm's law it back to get the resistance, right? So what we're going to do is we're going to make the input of our equation, and I'll show you how all that goes down here in a second. The input to our equation is going to be our resistance. We're going to find the resistance value that our thermistor is reporting via the ADC, and then we are going to plug that into an equation that should give us what temperature that correlates to. Now, where do we find the equation is probably what everyone is asking right now. So this is how you do it. in Excel, first things first, we're going to plot it. Now, I'm going to, like I said, I put the resistance values as the first column because that'll be the X coordinate, and then the Y coordinate will be the temperature value. So all I did was literally just verbatim, one for one, copy this over there. Except one thing that I did change is because microcontrollers can only go up to 32-bit integers and things like that, some of these numbers can get gigantic if you're dealing with thousands. If you're putting in thousands of resistance and then you square it and then maybe cube it and then you take that and multiply it by this and multiply by that and then maybe square that, or it starts getting to be astronomical numbers, and you really need like almost like 64-bit numbers or maybe 128-bit numbers. Well, since most microcontrollers can't go that large, you have to scale things down, which all you do is just scale them by 10. That makes it easier. So what we're doing is, instead of putting in 7,500 and whatever, or 352, we're just doing 7.3529. Okay, so that way it's in kiloohms. Okay, so that's what we're doing for our scaling, to help scale this, so that way when we put it into our microcontroller, it's not too big for the micro. So if you guys notice that the numbers are 7,352 and over here it's 7.3529, that's what I'm doing. I'm just moving it by an order of magnitude. Okay, so let's get this out of here. So what you do is you can just select this whole group, is what I do. If you come up here, I'm using the new version of Excel, but this works on pretty much any version of Excel. Go to Insert here, and we're going to want one of these scatter plots. Okay, so you're going to want a scatter plot. I'm just going to do a basic scatter plot, and see there's what our chart's going to look like, what our scatter plot looks like when you plot it. So for every given, remember, resistance is on the bottom, temperature's on the top. Obviously, it stops at 50, right? That's where we stop, and that's below 1. So that makes sense. Now we need to find an equation. Now, one cool thing about Excel is it will do regression, is what this is called. I don't know if any of you have seen that in math, but there's what's called, there's linear regression, there's quadratic regression, polynomial regression. There's all those different forms of regression. Well, if you click on the data points, see how it selected it? If you click on the data points and then right click, you can come down here to add trend line. You add the trend line, it'll bring up a wizard. For me, it's over here, so most of the time it pops up a window in other versions of Excel. And you have different lines to choose from. Now, as you can see, this line doesn't exactly fit the data. We want a line that runs right along with the data. So linear is probably not going to do it. Click on logarithmic. It's pretty close. It's pretty close because the most thermistors and thermal components and stuff are based on a logarithmic scale. So logarithm's going to be close. But if you really want to get really precise, go over here to polynomial, and like me, I did third order. That's pretty darn close. So what you can do is, now that it's found a line, you can see the equation by coming over here and say display equation. And I also, and see it puts it down here, we'll move it up here where we can see it. I also like to display, whoops, click on the line here, display the R squared value, which what this is the correlation coefficient. Sorry, try saying that 5 times fast. Anyway, what that tells you is how well the data is correlated. Perfect data correlation, which means that the line fits absolutely perfectly to the data, is equal to 1. So we're at 0.9977, so that's pretty close to 1. Okay, so we're going to take that, and that's going to be our equation. If you look at the top here, that's the equation. Let me see if, I don't know if I can make this bigger or not. Come on now. Can I scale it? Can I scale it? No, I can't. Okay. Well, I can do this. I can zoom in here. Let me zoom over here. Let's get this out of the way. Get that out of the way. Okay. So there's our equation. So negative 0.2947 x cubed plus 4 point that x squared minus that plus that. Okay, this is going to be our equation that we're going to use. If you put in any value of resistance in for x, then the y will be what temperature it will be. So this is very important. We have to remember this. Okay, so I'll see if I can't maybe flip back and forth between this and the other stuff. Let me just move this down out of the way. Okay, so now we're going to go ahead and fire up our programming language, which for me, bust out the good old VM box. Oh, whoops. I got to remember my password. Give me a minute. All right. So here's our code, okay? And like I said, all of this code will be posted for you guys to download if you want to download it, tweak it, play with it, do whatever you want. This code is written just the way the hardware is. You might want, like I said in the hardware video, you might want to add an extra potentiometer if you want to adjust the value that it's going to be shooting for. So if you want to adjust the temperature, then you need to do that. That's what this is. We come down through here. Here's all of our defines. There's our relay. We're defining that on RB5. But our temp set, what that is that's the temperature set. I want it to be about 5 degrees Celsius, let's say. So that way it'll, I mean, this thing's not going to be perfect, but 5 degrees will keep it away from being freezing, from accidentally being freezing due to rounding error and whatnot, and it'll also keep it from being too warm. So 5 degrees is about perfect. So, but that's what I set it as. Like I said, you could take this and not do this and just put in another, hook up another ADC channel to like a potentiometer or something, and then calculate based on that, a number, a degree C or something based off of that, however you want to scale it. And then you could basically twist a potentiometer and change the target set point for it. So that's what we have. So our target is 5 is basically what that is. So we're going to pop into our main function, set up our tri-state registers, set up our analog select where we only select the one analog in, set up our other analog registers. Then we're going to initialize our LCD. I am using an LCD.h and LCD.c files. Like I said, these will all be published, but that has the initialize and all, the initialize A to D, because that's the next one. All that stuff is in those. The functions.c, we'll be going into this here in a minute. That has all of our A to D and all of our LCD stuff and other LCD things and whatnot in it. So I'll be going through it all. So anyway, so we initialize the LCD, initialize the A to D, we delay a little bit, and then we go ahead and we write our first thing. I'm going to clear the LCD. I'm going to LCD go to 0, which is basically the top left corner, and I'm going to put the temperature sign. Then I'm going to go a little bit further and add the character DF, which, I can't remember what that actually is. I'd have to look that up in the character map. I didn't put a comment in. Sorry. May have to wait till the demo video to see it. I believe it's the colon. I think it's the colon is what DF is the colon. But, don't hold me to the fire on that one. I don't remember. I think DF it's the colon. I'd have to look it up in the character map. And then, obviously, the C. Oh, no, it's the degree sign. That's what it is. DF is the degree sign. Hexadecimal DF is the little degree symbol for degree C. Then we go to 40, which is the next line. We do our set. Then there's our degree C. Okay, so I could type that in there. Anyway, so we set up basically where we're going to put, and see there's that temp set. There's our temp set that we're putting. I'm going to display that as well. And then we're good. Then we go into our for loop, and this is where we're going to go ahead and we'll print out our numbers. So we're going to go to 02, which is basically it's going to put it where we're getting ready to write the temperature. Then we're going to read the ADC value, read channel 0. Then what we're going to do is see, this is a 10-bit ADC, so those of you that have seen my ADC videos and stuff, that gives you 1024 counts, in 0 to 1024 counts. So basically you're taking, I just remembered this number. What it is if you take 5 volts and divide it by 1024 and whatnot, you get about 4.88 millivolts per count is what you get. So that's what we're doing, is we're taking that number, that 0.00488, which is about 4.88, 28125 millivolts, and we're multiplying that by whatever the ADC read is. So if it comes back, 1, then it would be 4.88 millivolts would be what it would be. So we're converting that number. So now we get the voltage value. We know the voltage now from this line, so we know the voltage. And now if we know the voltage, well, with the volt divider that we have, we can calculate, by going backwards, we can calculate the resistance of it. So let me see. I don't know if I can do that here. Well, basically you can see it. Basically a volt divider circuit. Now I better draw it. Give me a second, because we have basically a 10K, right? So what we've got going on is we've got, oh, this is going to be fun again, a resistor and resistor, basically. Essentially, we can change one of them. Like this one. This one's our thermistor, right? Okay, this guy is 10K. If I can draw it, 10K. This is so hard doing this with a mouse. Anyway, if that's 10K, so what we can do is, and then you have a certain voltage. Well, if you want to know the voltage across this 10K resistor, so essentially you want to know this voltage here, you want to know what this voltage here is, okay, what you're going to do is our input voltage is 5 volts, right? So what we're going to do is we're going to take our input voltage times the resistance of the one that we want divided by the sum of the two resistances. Now this one we don't know what it is, so we're just going to call it, oh my good heavens, we're just going to call it R. I tell you, this is really difficult with a mouse. So we're just going to call it R, okay? So essentially we have 5 volts times our 10K, I'm trying to make this as pretty as I can, divided by the 10K plus some R, okay, is going to equal our V sub 0, and we'll call that V out. Well, since we're using an ADC, okay, we know what V out is because our ADC will you know, we can calculate and it'll tell us what the V out is. In fact, we just did that, you know, right up here on this line. This line calculates what that voltage is, okay, that it's measuring. Well, based on that, based on that voltage, go back here. We know what V out is. Well, if we know what V out is, the only unknown is this R right here. That's the only one we don't know. So using math, you can solve for this, and you basically, let's see if I can do this. I'm gonna try to do it in my head, so this could be scary. So the first step would be you got to move the 5 volts over. So we're gonna have our V out, and it's gonna be divided by 5 because we have to move our 5 volts over. Then what else can we do? Let's see, that's gonna move over there, and then that's going to be equal to our 10. Excuse my horrible handwriting. Over 10K. Ow, plus this R that we don't know. So now you can see we could take and, let's see, we'll move those over. So you're basically going to have your 10K plus your R. Be over here. You're going to have your 10K divided by your V out divided by 5 volts. Good grief, this is getting crazy. So then all we have to do is just move that 10K over, and essentially, since you're dividing, it's the same thing as multiplying. So technically, if I can do this, good grief, it's going to be our 5 volts times our 10K. Put that in parentheses. Our V out, and then we've got minus the 10K. Okay, hopefully that made sense. It's a little shaky, but this is basically our end result. This is what we wanted. Woo! Is that. So if you look back now, it's essentially what we're doing. There's our 5 times our 10, 5 volts times our 10K. Okay, now here's where it's important. Remember me telling you that I moved everything. I moved all those when we did the, let's see, let me get this, will this work? When I moved everything over, remember I moved it over to where it was K, it was kilo ohms now, and to save us the problems later on of having too big of numbers. Okay, this comes into play along with this part too. I'm using the 5 volts times, and I'm just doing times 10, okay? I'm not doing the 10,000 and putting the 3 zeros on it, because this essentially is going to serve as our X value in our equation, and that's going to be the next step. Will be putting this resistance value into our equation. Well, if that resistance value is in actual thousands in our equation is set up for kiloohms, you see it's going to be way off. It's going to be way super off because it'll be this huge number that we're putting in. So we have to make sure everything stays within scale. So we've got 5 times 10, and just pretend that there's like a little imaginary K. There's a little kiloohm symbol right after that. So 5 times 10 kiloohms divided by our analog value that we calculated up there, which is basically our V sub out, right? And then minus our 10K, right? Just like, let me see if I can get this and make it small so we can somewhat see them both. Okay, yeah, we can kind of see them both. I'll cut it off here and you can see both of them. Okay, so see, there's our 5 times our 10, 5 times our 10, divided by our V sub out, okay? And then that whole thing minus the 10, okay? So there's our equation for finding the resistance, okay? So there we go. So first step is read the ADC, convert that to a voltage value, back to, you know, an analog voltage value. Then we're going to calculate the resistance based on that analog voltage value, okay? And then let me get this out of here. Now it comes time to play with the equation, okay? So let me get that over here. Let's see if I can do this. Maybe I can scroll this over and you can see all of it. Maybe. Can I get it all in there? Yeah, I probably can if I do this. If I move this over. Come on. I want to get all of it in there. Hold on. Let me move this over so we can get it all. That way we can see it on both pages. Dealing with dual monitors and everything is a real pain. Hey, there we go. Success. All right. Now, what we are doing here on this next line, pop this back up, is we are basically building our equation that's over here. We're building it in code, okay? So to do this, you will definitely need to include the math library, okay? It comes with the High-Tech C compiler, okay? So you definitely got to include the math library. Otherwise, it won't know what this LDEXP, that's basically the caret key, essentially, is what that is. That's so we can enter an exponent. So you need that function that comes with the math library, okay? So first off, we're going to say, all right, there's our minus. See, we got minus 0.2947, so minus 2947 times. Now, here's how this works. This is a cubed in here, and you're noticing that I've got a 2 in here. Well, the reason being is because in this function, it counts the 0, I believe. Yeah, so it counts the 0 in this function. So you can do a x to the 0th power. So it counts that as the first one. So if you put a 1 in, that's basically the 0th power. You put a 2 in, or no, the other way around. Sorry. You put a 2 in, and that's like going to the 3rd power. You put a 1 in, that's like going to the 2nd power. And you put a 0 in, it's like going to the 1st power. So my bad, I think I said that wrong. It doesn't count the 0. So that's how it works. So if I want to cube this, then I put in a 2. Okay, and then plus our 4.7297 times our resistance, then squared, and you, like I said, since it doesn't count the 0, you have to subtract 1, so 1, and then minus 28.316 times x, and x is our resistance, okay, times x, plus, and now you see that this isn't perfect. This is 70.238 instead of 68.238. That's because once you get this together and get it start working, you'll need to calibrate it, basically. You need to find something cold, put it in your fridge or whatever, and get a known thermometer and measure it, and then if it's off, you can just increment this number. You can either increment or decrement it, add one to it or take away from it, until you get it to where it matches your thermometer reading, your known working thermometer reading. And so that's what I've done here. I've already kind of calibrated mine. Yours may be different. This number may be different. 68.238 may be perfect for you. That's something to play with. That's a number that you can play with because it's just adding on to the whole. So that way you can add linearly, and kind of bump your settings around if you want to adjust it. That way you don't have to use another trim pot if you want to. But if you wanted to use a trim pot on that thermistor resistor volt divider circuit there, you could use a trim pot on that and effectively do the same thing. But one way, you can trim it in software by just editing this number, or you can use a trim pot, however you want to do it. But that's basically what we're doing there. So that's how we put the equation into our calculation here. Now that's our actual temperature. Now we're ready. Now we're going to print num, and I put decimal because there's a couple of different ways of printing the number to the screen, because the screen takes in the ASCII number, whereas if you just throw in like a character or whatever, it's actually a hex number, and so you have to have some sort of hexadecimal to ASCII converting to go on to get it in there, and that's what this function basically does, which you guys, like I said, all this code will be posted. I'll show you. You guys can look through it and see. But it actually does a hex to ASCII conversion, so that way the ASCII gets printed to the correct hexadecimal number that corresponds to the ASCII character that you want, gets thrown to the screen. And so then that prints your stuff out to the screen. And then, of course, here's our relay circuit right here. I'm going to say if our temperature is greater than, let's say, +5 more degrees on top of whatever our target set temperature is. So basically, in this case, since our target set is 5, it's going to be if this gets greater than 10, then it's going to turn our relay on, which kicks on the refrigerator, and then, or freezer, whatever it is. And then otherwise, it's going to check to see if it's less than or equal to the temperature set, so less than or equal to 5 degrees, then it will kick it off. And then, of course, in any other situation, any weirdness beyond that, it'll just keep it off. So that's essentially it. I can build it just so we can make sure that it builds properly. Yep, build successful. And check this out. Even with this gigantic equation and everything, our memory usage is actually pretty low. Got only 24% RAM, 40% flash. Doing pretty good. So anyway, guys, hopefully this video hasn't gotten too long, but I wanted to show you where everything came from, and like I always do, walk through the code with you guys, because so many people just slam code out and say it works, and you get it, and it doesn't make sense. You don't know what they're doing, and you try to make it work, and it doesn't work, and you really have no idea what to change. So I like to kind of roll through the code for you guys, especially when it starts getting kind of complicated, and let you guys know where I come up with some of this crazy math. There is methods to the madness, I assure you. So don't get too worried. Alright guys, the next video up on the plate will be the demo of this little device. So I'll be showing you guys how it looks, how it was constructed, different parts and pieces of it, so that you guys can build your own if you want to. Alright guys, that's enough time for me, enough today. Please like, subscribe, share. That helps out so much because it helps me buy more equipment and things for you guys. The new stuff that comes out, new ICs, new embedded solutions, everything that comes out that everybody's playing with. I buy those up and get some videos going, get some work on those, and show you guys how to play with them and use them. So that really helps a lot. Like I said, if you haven't subscribed to me on Twitter, I'm also there. I try to post when I can. Especially if videos are going to be late. I try to at least release a video a week. It doesn't always happen, but that's my goal, and that's what I try for. And if it's going to be late or something, I'll post a tweet or something, let you guys know there. Also, Google Plus. I've had lots of people add me on Google Plus. Go ahead and add me on Google Plus. I post there sometimes, and actually, I think since my Twitter is like tied up with Google Plus somehow, whatever I post on Twitter goes on Google Plus, and whatever I post on Google Plus goes on Twitter. Or maybe only one way, I don't know. I try to keep my postings on both places because I've noticed there's quite a few people I've got on the good old Google+. But anyway, take care, guys. Keep coding, keep building, because that's what it's all about. That's what makes it fun. We'll talk to you later, guys. See you next time. Bye-bye.